Here we go. We're going to begin with our physical applications. We're into physics. I'm guessing that most of us students in a Calculus 2 class are not taking Calculus 2 because they're a math major. There's going to be a handful of us, of course. But most of y'all are doing this to become proficient in physics so you can, achieve your dreams, get the major you're looking for. So let's get into it. So we'll begin. Here we go, some physical applications, and let's start with this right here. Boom. So we need to understand the difference between force and work. Force and work. And that's what we're going to get into. But as we go, not in this first one, we have four main games. We're going to talk about Hooke's Law, which is springs. We're going to do lifting problems, like perhaps you're on top of a building and you need to lift a rope up. How much work is done? We're also going to talk about hydrostatic pressure. Oh, you know all about hydrostatic pressure, don't you? Yeah, but hey, we're going to learn something about it. And then we're going to do some pumping problems, where maybe you got something in got some water, and we're going to pump it out. And we're going to see how much work is done to do that. Hey, that looks like a drink. So maybe you're sucking the drink out. Maybe you got yourself a nice little margarita or something. You want to know how much work is done by putting that margarita in your belly. All right, let's get to it. So let's start focusing on the difference between force and work. Now, force, typically written in this way, force is equal to mass times acceleration. So we're going to talk a lot about that. But for many of the things we're going to do, it's going to be, do you know an acceleration that's natural? Grab a pen or something and then drop it. There's this acceleration called gravity. So we could have force is equal to mass times acceleration. We could have force is equal to mass times, it's still acceleration, it's gravity. And man, we're going to play around with what mass is as well. Then we're going to talk about work. Now, work has to do with how much force is being done per some unit of distance. So let's read what force is. What's the definition? Well, first off, we need to know what are our gosh darn units. You know what I mean? What's our units? And we're going to use, this is in the SI units, or you can think of it metric system. Because in sciences, we don't mess around with that British imperial system of feet and pounds and stuff. We can. Most certainly we can. But since we're science people, you know what I mean, STEM majors, let's talk about the metric system. So we're going to talk about newtons. Newtons are a unit of force. A newton is the force required to give a 1 kilogram mass, so an object that maybe weighs 1 kilogram, an acceleration of 1 meter per second squared. And that might be a little rough to kind of picture, but just hang on. Hang on. Now, what do we got now? We got joules. Joules are our unit of work. We'll be using a J. A joule is 1 Newton meter. So it's saying, 1 Newton. Well, newtons are a unit of force. So it's, so 1 Newton force per meter. This is the work done by a 1 Newton force acting over a distance of 1 meter. So possibly you got something right here and we want to move it 1 meter. Well, it's going to be a joule would be if it took 1 Newton of force to move this thing 1 meter. Now, I'm going to tell you something, to be perfectly honest. I'm a math teacher. I am not a physics teacher. I am not professional with this. But I'm trying to get you ready so when you're into your physics courses, when you're with a professional, you're going to have the math pieces down a little bit. So I have rudimentary knowledge of this. I know the basics, but I do understand the math behind it sometimes. So, yeah, hopefully this works out. So let's start to see something. Here's our definition. We're going to see an example too. So there was what I was describing here. So maybe the force changes. Maybe it takes a different type of force. Maybe it takes more. Like maybe you're pushing something along a smooth surface, and then you get to something that's a tougher surface, and then it gets smooth again. So it's going to take more force. If you were to push a box along a smooth surface, it wouldn't take much, right? It would just move right along. But then once it got onto like gravel or something, it's like, oh, we need more force to push this. And that's kind of the game with a variable force. There might be things acting upon stuff. And in this section, we ignore so many things. We ignore so much. But that's how we learn physics. If we didn't start with the basics, it'd be way too much to try and learn. So this is just our basic game. And this is big. This is big. The work done by a variable force, F, moving an object along a line from x equals A to x equals B in the direction of the force, well, we'll say the work is the integral from A to B of that force function. From A to B of our force function. And of course, we're going to do this all in terms of x. So let's see an example. Now, this is a very rudimentary. Do not expect anything like this on exams. This is just to get us started. So how much work is required to move an object from x equals 0 meters to x equals 3 meters? And this is what we're talking about, our position function, right? We're talking about the position. So we're assuming on maybe like an XY graph, we're going to start at x equals 0, and then we're going to go to x equals 3. Now we continue moving, and we're like, okay. Now this is in the presence of a force in newtons given by f of x is equal to 2x. So really this function that we have is just this line. Y equals 2x. And we're going to find the area under said curve. Okay, let's check it out. So following the formula, there's not much to do here, right? The work is equal to the integral from 0 to 3 of our force, learning to speak, our force function, 2x dx. And you can see how this one's nice and cooked up. We take the antiderivative, we get x squared, right? The 2's cancel out. We go from 0 to 3, so we have 3 squared minus 0 squared is equal to 9. And we're super stoked on ourselves. We're like, whoa, look at this work I did. I'm so happy I got the right answer. But you don't have the right answer yet. We have to use units. Anytime we're in this physical applications, we need to use our units. And throughout your homework, it's probably, I don't know if it does it on every problem, but it might just give you the units. On an exam, we must state that since we're talking about work, it took 9 joules. And I use the same example all the time. If I ask you, hey, how far do you travel to go to work? And you say 7. I'd be like, 7? 7 what? 7 miles? 7 minutes? What are you talking about? Or I ask you, how tall are you? And you're like 6. I'm like, come on, dude, answer the damn question. So when we're asking these word problems, you don't need to write a sentence back and saying, well, the force required. Would you actually, if I asked you, how much work is required? And you're like, oh, well, the work that is required to move us. No, you wouldn't answer like that. You'd say, hey, it took 9 joules. That's all we need. You just need to make sure that you use your units. So there's an intro. We're going to start moving back into, we're going to start with Hooke's Law. Hooke's Law is going to be next, and that's all about springs. Trust me, you will want springs on your exam. They're typically a little simpler to understand than the lifting, the hydrostatic pressure, or the pumping problems. If I was to put this in order of difficulty, I'd probably go 1, 2, 3, and 4. And 3 and 4 can be, depending on who you are, could be switched. But typically Hooke's Law is the simplest for us to understand. And maybe not at the beginning. All this stuff's tough to understand. But it will get progressively more complex. So here's our games. I'm done talking for now. I will see you in the next one we talk about Hooke's Law.